of this epsilon. Okay, so like this thing. So I'll put it as x0, the unperturbed part of the exact solution. Okay, then the first order correction, then second order correction. Okay, and so on. Clear? So this is a series extension of this very solution. Okay, we are just doing this kind of problem. Many people were not here yesterday. We're just trying to solve this kind of problem in a different way. This equation is very complicated to solve. Okay, so let me repeat it again. Okay, so put epsilon equal to 0. So what is the equation? So it is x cube minus 4x equal to 0. Clear? So what are the roots? 0 and plus minus 2. So these are the exact solutions of this very problem. Now if I am having a kind of equation like this thing, how to solve this kind of equation? Clear? Okay, so what I will do, so we can guess the nature of the solutions of this very problem. We can say the solutions of this very problem depend upon this kind of parameter epsilon. Okay, and this epsilon is a very small quantity. Okay, and I can now extend this solution in terms of these. I can have a series extension of this solution around the point x0. Okay. So x0 is your exact solution, and I am trying to figure out what are the corrections to this x0. Okay, if I am adding a small quantity in this very equation. Clear? Okay, so now let's substitute it back to this very equation. Okay, so substitute it there. So what you will get? Okay, q, okay, minus 4 plus epsilon, this objective. Then you are going to accept epsilon equal to 0. Now how to proceed? What you will do, since, okay, so you can expand this thing, okay, and rearrange the terms in the order of, in the powers of epsilon. Okay, so you will be having like this thing. So you will be having a term of the order of epsilon naught. Okay, that means first order term, you will be having a term of the order of epsilon and of the order of epsilon square and so on. Clear? And we know all these epsilons are linearly independent of each other. Clear? Okay, so let's write. Okay, so let's expand it. So put okay, cube it. So what is the first term? x0 cube. What will be the another term? 3x0 square. Then you are having x1. So it will be of the order of epsilon. Okay, so other terms will be epsilon square. Is it? Okay, so let me put dash dash dash. Okay, minus. So let's extend it. What you are having? 4x0 plus epsilon 4x1, then plus epsilon x0 plus a term of the order of epsilon square. Clear? Okay, plus twice epsilon. Rearrange the terms. So which is the term having no epsilon at all? So you are having x0 cube, okay, minus 4x0. Clear? So what is the power here? What is the factor here? Epsilon raised for 0. Clear? So it is the order, 0th order term. Now let's take the epsilon term. So what are they? 3x0 square x1 minus 4x1, then plus x0 plus this 2. Okay, because this is epsilon order term. Clear? So then you are having the terms epsilon square dash dash and then other order term. Clear? Got it? Now how to solve it? How to solve this set of equations? Okay, since all these epsilons are linearly independent, I can separately put this equal to 0, this equal to 0, and so on. Clear? So let's take the order of 0, this very term. So what it gives me? Is 0. Clear? Got it? So what is the solution? So what that you got? Plus minus 2. That is your unperturbed solution. The exact part of the solution. Clear? Okay, where from now the corrections will come? Corrections will come from here. Now look at the order of epsilon equation. So what is the equation? 3x naught square x1 minus 4x1 plus x naught plus 2, that's equal to 0. Now look at what is the correction we need to figure out. X1 is the correction to the solution, is it?
Yes.
Okay, I know the epsilon. Epsilon is a small parameter. Okay, I can fix the epsilon later on. Okay, I need to figure out what x1 is. Clear? So now look here. So this very solution x1 depends actually on the x0. What is your original solution? Clear? So how many solutions you are having?
2.
Because it's a cubic equation, you are having 3 equations. Now let's look the effect on the first solution, x equal to 0. Okay, so take this solution, x naught equal to 0. So let's look at this very equation. I will define this thing, x0, 0. And this superscript means it is the 0th. No, not order. It is 0. It denotes this 0. Clear? Okay. So let's look at this very solution. Okay? So now let's use this x0 where? In the order of epsilon equation. Clear? So substitute. So when you use it, so let's call this as equation 1. This as E. Using equation 2, what you get? So first term is 0 minus 4x1 plus x0. What is x0? 0. Clear? Plus 2 is equal to 0. So you are having x1 equal to minus 1. Okay? So now look at the solution. So now I can say this solution, let me write x is equal to x0 plus epsilon x1. Okay, plus order of epsilon square. Higher order terms. So clear? So what is your x0? That is 0 plus epsilon is, so it goes like this thing, epsilon by 2 plus order. So this is the first order correction, 1 by 2. You got it? So that means your 0, the solution that was 0, it gets shifted by how much? Epsilon by 2. Clear? Similarly, you can calculate if you go ahead, take epsilon square term. Clear? So you will be having a order of epsilon square equation, and you substitute these things, x0 as well as x1 there. Okay, it will depend on actually x1. So once you substitute, you will get a correction of the order of epsilon square. Got it? Okay, so now let's look at this one. So if I have this x0 equal to 2, let's define it as x0. So this is also the solution. Now let's look at the effect of this perturbation on this solution. Clear? Okay. So let's look. So substitute x0 equal to 2 in equation 2. So what you get? So 4, so it is 12 x1 minus 4 x1 plus x0 is 2. Plus 2 is equal to 0. So how much is that? There is an error somewhere in this very equation.
Sir, it's 1
It is minus 2. Yes,
plus
yes.
1 by 2.
1 by 2, not. Huh?
It is 1 by
Yes,
2.
it is
Plus
1 by
1
2.
by 2.
Yes, good. Great. So, no, I mean, is there an error in this very equation? 8. So,
4.
there is an error in that equation. Probably.
So minus x naught. Minus x naught.
Hmm?
So minus x naught you want.
Can't be. Yes, minus x naught. Okay. Yes, it is a minus x naught. Yeah, great. Okay. So it's minus here, and rest is okay. Okay. So it's minus by this thing. This cancels. What is your x1? 0. So that means there is no first order shift of the solution. Clear? So this solution remains as such. It remains intact. Got it? So what is this solution therefore up to first order? So x equal to, so x naught, okay, 2 plus, okay, epsilon x1, so plus order of epsilon square. Okay, so what is x? So it is 2 plus 0 times epsilon. So it means you don't have any kind of change of this solution. Got it? Okay, so now let's take the third solution. Yes. So let's take the third solution. So you are having x0 equal to minus 2. Let's define it to be x0 minus 2. Clear? Okay. So use x0 minus 2 in equation 2. What you'll get? Just
12x.
yes. What is the first term? It will be as such. 12x1. Then minus 4x1. Then minus, so it is plus 2 equal to 0. What is x1? Minus
1 by 2.
minus 1 by 2. Okay? So you do algebra yourself. Okay? So what is there for the solution? So x is equal to minus 2 plus, minus epsilon by 2 plus order epsilon square. Got it? So I can say up to the first order correction, the solutions of the equations okay, so I can say you are having this very equation. So its solutions are what? What are its solutions? Huh? Just tell me. So solutions are x is equal to, the first term is 0, then plus epsilon by 2 plus order epsilon square. Another is 2 plus 0. Okay. There is no first order correction, plus order epsilon square. Then you are having minus 2 minus epsilon by 2 plus order epsilon square. So this is the solution of your problem. That means if you substitute these values in your equation, so they are satisfied up to order of epsilon square. You have to ignore order of epsilon square terms in your equation. Clear? Got it? Okay, so the assignment for you people is calculate up to the order of epsilon square. You have to take the square term as well. So let me put the square term. So this is actually the solution up to the order of, okay, epsilon square. So it is 0 plus half of epsilon, okay, minus 1 by 8 epsilon square. And you have to ignore the order of epsilon cube terms. Okay, 2 will remain as such, 2 will not change. Okay. You have to show this thing, minus 2, minus epsilon by 2. Okay, sure. So this is the answer. This is very simple. You need to calculate the order of epsilon square equation. And in that very equation, substitute these values. Okay, any question till now? Everybody had got the idea of perturbation? Huh? So if you don't have any question, let's proceed with our problem. Okay? So let's go to our in a formal way, perturbation. Okay, so we are doing time independent case. We are not. So it is time independent. We don't assume any dynamics. Okay, clear? It is sometimes also known as static perturbation. Okay. So you don't consider any time dependent phenomena. You just look at what? Time independent. Okay, static phenomena. What does that mean? So you don't consider the evolution in time. Huh? Okay. So you are solving actually the Schrodinger equation without time dependence. Huh? So let's Okay, so what I have done here, I have introduced actually a parameter epsilon. Clear? Okay. So we will also introduce a parameter here in our Hamiltonian. So let's try our total Hamiltonian of the system. Okay, of the energy of the system in two parts. Okay, so let me explain again. So I will introduce some parameter lambda. Let's try H1. Okay, so let me tell again. So we are having certain kind of problems. Okay, in quantum mechanics, only a few problems are exactly solvable. We don't have many problems that can be exactly solvable. What does that mean? We cannot solve all the problems for its complete set of eigenstates. Only a few problems are known to us for which we can solve them for its complete set of eigenvalues as well as eigenfunctions. Clear? Suppose you are having a particle in box. You know its all the eigenenergies. You know its all the eigenfunctions. You have harmonic oscillator in one dimension, let's say. So you know it's all the eigenstates as well as the eigenenergies. Clear? But let's say if you are having a particle that's going through a shallow well, okay? So the number of eigenstates or the number of bound states will depend upon the height of the well, is it? You are not able to solve that exactly. So you have to make approximations for that very well. Clear? So although looking as you are having a simple problem at hand, but you are not able to solve that exactly. Is it? It will ultimately depend upon the what is the how much well is shallow, okay, how it is deep, how much it is deep. Clear? Got it? Okay. Now let's say if you are having a harmonic oscillator, you put some enharmonic terms in it, it is not solvable exactly. Clear? Okay, or let's say you when you approximate the harmonic potential about a local minimum, you are having certain kind of potential. Okay, a particle is trapped in that potential. The first approximation what you make, you say there is a local minimum, is it? And you get the quadratic form of the potential. Clear? But there can be certain non-linearities as well. It's not necessary. It's a stable kind of minimum. You can be having some non-linearities. Okay, deformation of that very potential will arise. Solving such kind of problems is very difficult. Okay, in principle, you can solve in principle. There are set of rules, but practically they are difficult to handle. Clear? Okay, so what is a method to solve? You rely on certain kind of approximations. Okay, we have done that kind of approximation in that equation. Okay, known as the perturbation theory. Okay, so what we will do, we will actually break down the total Hamiltonian of the system into two parts. One part is the exactly solvable part, and another part we will treat as a perturbation. Okay, we'll say this part, the magnitude of this very part is very small in comparison to the magnitude of this part. Okay, when we say the perturbation itself means the disturbance is weak. Okay, you got my point? So if it is, let's say, if the magnitude, okay, I'm saying roughly, okay, if the magnitude of this very term is of the same order as this very term, so then we cannot apply the perturbation theory. Clear? So its magnitude must be small. Okay, here I have introduced a parameter lambda with which we can control actually the perturbation. Look here, we have introduced here parameter epsilon. We have controlled the perturbation. What does that mean? We have actually explored in powers of this epsilon the solutions of the problem. Okay, so let's say if you put epsilon equal to 0, so that means there is no perturbation in this very equation. There is no, these kind of terms. When you put epsilon equal to 0, you get your usual solution, is it? If you put, let's say, full perturbation, let's put epsilon equal to 1. So you will get a different thing. Okay, you will get the effect of the perturbation. That means if you change your epsilon from 0 to 1, so you are actually introducing the perturbation in the system. Okay, so that means it acts as a control parameter in the system. Clear? In your calculations. So this lambda is same thing. Okay, it is doing the same thing. Okay, we call this lambda as a coupling constant, but we will call it simply as a parameter. Okay, here I have introduced it by hand, but in most problems, when you do physics, the realistic problems, you need to figure out what this lambda is. Okay, let's say I will give an example. You have heard about the quantum electrodynamics. Is it or simply the coupling of radiation with the matter? Clear? if you are doing the perturbation theory, what would be the suitable coupling constant? It turns out to be the fine structure constant. Okay?
Yes.
Clear? Okay. So let's write what is the energy here. Okay. So the energy will be simply the function of this lambda. Clear? Okay. So let's put a qualitative idea of what is happening. Okay. Let's put it qualitatively. So let me plot. Listen. Suppose this is 0. So this is your lambda. Along this very axis, your lambda, your energy. Your lambda. Okay? So when I am at, let's say, lambda equal to 0, that very term is not there. The problem is exactly solvable. Okay? Let's say at this very point, okay, let me write at this very point, you are having some solution. Clear? Okay, it can be degenerate, it can be non-degenerate. The perturbation what we will be doing for the time being, it is non-degenerate. But here I will show the degenerate case as well. Okay, so let's say you are having another solution. Okay, when you don't have the perturbation, you are having some degenerate levels. Okay, like this thing. So these are all the degenerate levels. So cross means you are having 2 states corresponding to this much energy. Okay. So here means you are having 4 states corresponding to this energy. Can anybody give me an example of this thing? Where the simple problem where you have degeneracy? In hydrogen atom simple. You are having 2p, 2p and 2s. Are they degenerate? Huh? Their energy is same. Clear? Okay, so you are in 4 states there. They are degenerate. Right? Okay, but here I have considered some, it is an artificial way. Right? Okay, so now let's turn on the perturbation. What will happen to the energy? Since energy depends on, okay, in principle it depends on this lambda. Clear? Okay, so let's draw the curves. Okay, so let me write some lambda is equal to 1 here. Okay, so it will depend on certain way on this kind of thing. Lambda, the way you vary it is not necessarily, it is this true curve. It's just the schematic representation. Okay. Now what will happen? So this once you turn on the perturbation, so what will happen? Yeah, so these levels can split up. Okay. So you can be having, let's say, like this thing. Okay. One level can go down. Okay. Another can go up like this thing. Okay. So when you put the full perturbation on. Okay. Any example of this phenomenon happening? Splitting of lines? Zeeman effect, you know, is it? That's actually, if you don't put the electromagnetic field there or the magnetic field there, you don't have the splitting of the lines. The degenerate states will appear as such. Clear? You put the field, the splitting of the lines will depend on what? How strong your field is. Clear? So it is the same thing. You can think the field as a perturbation. So you are changing, let's say B acts as this lambda. Clear? Okay, similarly this can happen. So there can happen like this thing. This can come here, okay, or the other point, let's say, okay, or you can be having the level crossing as well. Okay, this can go this way. Okay, so this is the the effect of this perturbation. It may induce the level crossing. Level crossing means 2 levels will cross. Clear? Okay, so you lower down the you turn on the perturbation or you turn on this disturbance in the system, so there may occur line crossing as well somewhere. Huh? Okay, it's not necessary all the systems possess this line crossing. Clear? So this is actually the effect of the perturbation. It will just allow you to get the idea of where the energy levels are or how the energy levels are affecting. Clear? Got it? Okay, good. So now let's go ahead. Let's move ahead with this very thing. So I will denote, okay, so let's assume unperturbed. So when I say the unperturbed states, so it means these are the states of this S0, unperturbed eigenstates. So let me write of S0, let me write this N0. Clear? So when I put the script 0, it means it is an unperturbed state. Clear? Okay. So with energy, so I am having the energy. So let me write En0. So what we are doing, I will fix one level of the system. Clear? I will fix one energy eigenstate and I will see what is the effect on that very level. So this very index will give me that level. En, so this n. This n is an index representing the nth level. Okay, 0 index means it's an unperturbed. There is no perturbation on this very level. Clear? And corresponding to this very level, you are having En. Got it? And 0 means what? So it is superscript. It's not the power. Huh? Got it? So what it means? So I'm assuming this kind of objective. Okay? So let's go ahead. So our problem is to solve. So let's write these as now the full eigenvectors. Okay? On H. Got it? So with energy E. So I am having this kind of situation. H and is equal to E. So what we need to solve? This equation. Clear? So this equation we need to solve in a this is already solved for us. Okay, at hand. So we start with this very equation and we need to solve this thing, or we are having this equation as 0 plus lambda H1. Okay, and excuse me. Hello. To jest klasne. To nie jest klasne. This is one. Okay, so I have given you the idea how to start with the perturbation. Okay? Now, what to do? I have given you the idea in the example. What to do now? Huh? What is how to start with? We need to solve this very equation. Clear? How to start with? Yes, series solution. Clear? So what we will do? Look here. So this En will depend on this lambda. Clear? So in this n will also depend on the lambda. How you choose the lambda? Clear? You got it? So what you will do? The first step is so you expand this energy as well as these eigencats in terms of lambda as a power series of the lambda. Clear? Okay. So how we'll do? So let me put it this way. You are having step 1. Okay, so that you will understand it. So you make a series expansion, Taylor series expansion, I will say. Okay. So you will put this n to be equal to so the unperturbed cat. Okay. Then lambda n1. So n1 means the first order correction. Clear? Then lambda square n2. Okay. So let me put it in the summation notation. So let's write summation. Okay, m, so n. Okay. Okay. So then we expand this En in terms of so you are having En naught, the unperturbed energy, then lambda En, the first correction. Okay, so this means the first correction. N is here what? The energy corresponding to level n. Okay, so this is the level index. So you are having lambda square En2. Okay, so let's write it as summation of m. Let's write lambda m p n. Okay, everybody got it? Okay. So now substitute these two equations in equation 1. Okay, so use it in equation. So what you get? So let's write it. So you are having h0 plus lambda h1. Okay, then so let's write what is n?
Summation.
Okay, so we'll not use summation. I just given you, okay. So we can put it, we'll just use this expanded formula so that it is easier to follow. Okay, so I am having lambda n1 plus lambda square n2 plus 1. So, okay, so it is equal to, what is En? So you are having En naught plus lambda En1 plus lambda square En2 plus J dash, okay, multiplied by, okay, acting on this thing, rather multiplied, and what is it? So N0 plus lambda N1 plus lambda square N2 plus J dash, okay? Got it? Okay, the step second is to separate the equations at different orders. Clear? The way we have done. Okay. So we'll write, okay, just multiply. Let's act this on this very object. So I'll put, so which implies h0 acts on n naught plus lambda h0 acting on this n1. Okay, then I'm having lambda square h0 acting on n2. Okay, plus lambda dash. Then I'll go only up to the lambda square. Okay, order of lambda square. So first term is lambda h1 and naught. Then you are having lambda square h1 and naught. So that's equal to, yes. Anybody asking question? So you are having En naught. Then you are having this n naught plus lambda En naught n1 plus lambda square. So just in the simplest of the way so that you understand it. So then you are having lambda, okay, En1 n naught plus lambda square En2, okay, n1 plus dash dash dash, because that will be, other will be lambda cube term. Then you are having lambda square En2 n naught plus dash dash dash. Rest will be actually lambda cube term. Okay. Okay. So now the step second we'll separate out the equations. Okay. So let me write step 2. So separate out the equations. So we are having order of lambda 0 equation. Now tell me, what is the order of lambda 0 equation? So it is h0 n naught, that's equal to En naught. Clear? So you have to take, look here. So anybody who is not following, so you take this term on this very side. So it is order 0 term. Huh? So you put that equal to 0. So it means h0 acting on n naught is equal to En naught. Clear? Now let's look at the order lambda term. So you are having this very term here, this very term here. Okay. So let's try that. So order of lambda. So what is that equal to? h0 acting on n1 plus h1 acting on n naught. That's equal to, what is that? Order of lambda. So En naught, okay, n1 then plus En1 and naught, then you are having. So there must be actually 3 terms. So we are getting only 2 terms. 3 terms are, I think 3 terms. Is it correct? Okay. So let's go to the order of lambda square term. Let's go to the order of lambda square. What are those? So you are having h0 and 2 plus h1 acting on n1. Clear? So this is the lambda. What is on the right hand side? So it is En naught. Okay, n2 plus En2 n1 plus En2 Clear? So these are the equations. And so on. So you go ahead. Huh? So now you can see. This is an exactly solvable equation. This is equal to 0. And okay, so this gives you simply E n naught. If you take this this side on this, h naught minus E n, so this will be 0. Clear? What I mean by that? So this means simply okay, h naught minus E n naught. Okay, acting naught n naught. That's equal to 0. Okay, so it gives you the exact solution. So that means the first order, sorry, zeroth order correction provides you the exact solution. Clear? Okay, it does not depend on any higher orders. Okay, so it's independent of these lambdas. And now, where from you are having the lambda dependence or the correction dependence? From here, order of lambda. Look here. So this in this very equation you are having both n0 and you are having n1. Clear? Okay, so now what I need to calculate? If I need to calculate the energy from this very state, from this very equation, so what is the energy I have to calculate? It is the first order correction. This is also known to me. En naught is here, so it's known to me. So what is unknown in this very equation? It is En1. So what I need to do then? I need to make an overlap of En1 with, okay, if I take n naught on this side, okay, n naught and n naught, they are normalized. Clear? So then this gets free from this n naught. Clear? And there is actually, okay, so let me put it. So you are having, okay, so from, so let me write step here. So for you people, okay, so let's multiply on this, okay, multiply on left by n naught, like this thing, okay, multiply equation, so order of lambda term. What does that mean? You are having this n naught, h naught, n1, okay, plus n naught. So if anybody is not understanding, just tell me. So be careful when you write these equations, okay. Okay. Got it? Okay. Yes, I have forgot to mention when we started this theory. So I usually forgot things. So we are doing non-degenerate perturbation. We are not assuming any kind of degeneracy in the states that we will take later on. Clear? And the second point is we are assuming the discrete spectrum. I am not assuming any continuous spectrum. Okay? Got it? So these are the two assumptions what we are deriving here. Although they are valid for when we do the degenerate or the continuous spectrum. But in the case of degeneracy, there are certain subtleties. Okay? So we are doing only the non-degenerate case. Okay? Okay, so now look here. So I have, okay, so the assumption here I am making now. So the assumptions what I will make. So I will assume this unperturbed cat to be normalizer. Okay? Okay, so these are the assumptions. So I am assuming this n naught n, this is equal to I dt. Clear? So then that means the length of the vector n naught is equal to unity. It is a unit vector. Okay? So and I will assume this kind of thing. Okay? So n, so what is the index? So I will assume n k, this is equal to 0, where k is running from 1. Clear? So what does this mean? So I am using, these are all or orthogonal. 0. So these are 0 and 0 and 2. So let's say clear? Got it? Okay, so the home assignment for you people is show this assumption is consistent. Assumption is consistent. So there is a consistency in the set of equations. Okay, you need to prove this assumption at least. Okay, this is a suitable assumption. So there is a proof for it. It's a very little proof, but you need to think over it. I am assuming here, but you can prove it. This is a suitable choice. You can choose this thing. Okay, so let me give you a hint. You start with your linear combination, and you make a different kind of, show that two linear combinations are the same. Okay? If you start with one linear combination and another linear combination, and using this kind of assumption, you say both are the same. Correct? Okay, so that will give the consistency check. So it's not an arbitrary condition. Okay? So that's why, okay, so why I am assuming this kind of condition, look here. So since I need to calculate this En1, is it? And I am assuming this N0 is normalized, so this is equal to 1, and this is equal to 0 by this kind of assumption. Okay? So this object is now equal to 0, and this is equal to 1. Okay? Now let's look at this thing. So H0, it will act on this N0, right? Because H is a Hermitian operator, so it can act both ways in the same fashion. Correct? Since N1 is not an exact eigenstate of this H0, only N0 is there. Okay, so this will give me this part. Okay, so it gives me En0. Okay, back this N0. Okay, so if you are not, okay, so it's like this thing N0, H0, that's equal to En0. Okay, clear? So let's do it. So what you get? So just tell me. Yes. Oh, sorry. Then you are having N0. Okay. So you are having like this thing. So you are having N1, is it? So you will be getting N1. This is equal to 0. Clear? Samajh aawa? Got it? Okay. So what you have got? So you are having like this thing N0, H1, N0, that's equal to En0. So this is the famous formula in the perturbation theory. So what you got? The first order correction to the energy is simply the expectation value of the perturbation Hamiltonian. Is it? H1 is the perturbation, is it? Is this the expectation value? Is this the expectation value, everybody? Okay, so let me put it in that fashion. Okay. Okay. So you know only the coordinate space. Let me go to the coordinate space. So what I will do, so I'll introduce a coordinate okay, like this thing, N0. So I'll introduce a completeness condition in coordinate space, like this thing. So this is an identity. Yesterday I told you, you are having H1. So let's write it something x prime, because these are dummy variables, okay, and then you are having N0, okay. So you are having dx prime you take out, okay. So you are having N0 and x, like this thing. Let me do it for you people. H1 x prime. So then you are having what? X prime n. Okay. So this object is your energy eigenstate in coordinate space. Dx prime. So let's write it as psi 0. Okay, psi 0 x. So psi 0 means this. Okay. Okay. Let me put in like this psi n0. Okay, n corresponding to the nth state. So let's write it as H1. This is a matrix element. Okay, then you are having, sorry, it is a star. So one should be star. Huh? Yes. So this is psi n x and this is psi n star. Psi n star. Okay, x. Clear? Because this is a number now. Huh? So this is a number. This is a matrix element in coordinate space. So you can put psi star here and you can put it here. There is no problem. Huh? So is this an expectation value? Huh? Clear? Okay. So this is the in the coordinate space. So memorize this very formula. So you should memorize it. Huh? So there is no other chance. So let's get to a quick calculation. Here, a simple example. Okay. So let's consider a harmonic oscillator. What is the Hamiltonian? Let's consider a harmonic oscillator, and we have put it in an electric field. Clear? Okay. So like this thing. So let me take an example. So I am considering a harmonic oscillator. So P square by 2m plus half of m omega square x square. So let's put it in some electric field. Okay, some E. So that means this is a charged particle. Huh? Clear? Is this an electric field? Huh? It's an energy, is it? Is this the energy? This entire term should be the energy. Yeah? So this is a. Okay. Because what is E times E? That is force. Force multiplied by distance is what? Energy. Clear? Okay. So what this is? So you can write this simply as h plus omega a dagger a plus half. Clear? Minus this I can write E. What is x? So it is root of h plus m omega a plus a dagger. Can I put it? So in terms of the operators. Clear? Okay, so now let's calculate the. Okay, I know. So this is your h naught. Now this is your what? Lambda h1. Huh? Clear? So I will write this simply as your h1. So what is your h1 here? So it's minus E root of h cross divided by m omega a plus a dagger. So this is your perturbation. So you are, let's say electric field is V. So okay, think this way. You are having a charged particle, it's oscillating, an oscillator, a charged oscillator, and you put some weak electric field here. Okay, what will happen to it? So it will shift to the energy levels. Okay? Now let's look at the first order correction to the energies. So how the energies will change. Okay, so what are the energies of the unperturbed harmonic oscillator? So your unperturbed energy is like this thing, n plus half h cross omega for nth level. So it is nth level. Okay? Got it?
Yes, sir.
Okay, so now let's calculate the correction to the nth level, first order correction. So I'll write En1. So what is the, okay, so so it is what? Unperturbed states N0, and H1 is what? So let's write H1, and so what is that equal to? Minus EE. So these are numbers, so they come out. Okay, so then you are N0. Okay, so I will not use not. Okay, so so let's put not. So let's not confuse you people. So N0 is actually the unperturbed state of the harmonic oscillator. Clear? Got it? Okay, so how this A dagger acts on N0? So when you are having A dagger for the harmonic oscillator, what you get? Root of n plus 1, n plus 1. Clear? When you are having this n, so what you get? Root of n minus 1. Okay, so let's calculate it. So you are having minus E root of h cross by m omega. So let's say A acting on n0, it will give me root of n. So you will be having like this thing. Root of n0, okay, n0 minus 1. Another will be what? Root of n plus 1, n0 plus 1. Clear? So since, look here, so these two are not the same. Clear? So that means this is what? This is equal to 0. This is equal to 0. Clear? Because this is the overlap of two different states. Okay? So what you are having? So that means you don't have the first order correction to the energy. Okay? At first order, the energies are not corrected. So there is no first order shift in the energy spectrum of the harmonic oscillator. Okay? But when we will go to the second order, you will see the second order, you get a second order shift. Clear? Got it? Okay, let's say you are having an example. Okay, let's put this instead of let's change this the spring constant of this very problem. Let's go like this thing. So you are having some half of, okay, so let's say half of kx square. Good. Great. You said it? Oh, good. So let's put this half of kx square. Let's add it. I'm just adding what? One more potential. So quadratic, it simply means you have changed what? The spring constant of the problem. Is it?
Yes, sir.
Okay, you have just be, I mean here. Okay, so you have just changed the frequency of the system. Okay, so it will affect what? Your energy. So let's calculate the first order corrections. Okay, so you are having plus half here, k, you have to put square of this thing. Clear? So let's put k and k by 2 square of this thing. So let's calculate what this square is. So it's k by 2. So it is an operator. it's an operator product. You cannot put a square plus twice ab. So you have to put it this way. So a square plus a dagger square plus a dagger plus a dagger. Okay? It's like this thing. Anybody who does not know, so it's a dagger a into a dagger a. These are operators, and operators do not commute in general. These operators do not commute with each other. So you have to put a square, a dagger a square, a dagger square, a dagger and a dagger a. Clear? So now let's calculate the first order correction here. Okay, so let's use. So you are having first order correction En1. So that's N0. So what is this thing? So it is k by 2 will come out. Then you are having this a square plus a dagger square plus a dagger. So let me put a dagger a acting on N. So to simplify this very equation, okay. So look here. You know this a dagger, that's equal to identity. Okay. So it means a dagger is same as a dagger a plus 1. Got it? Okay. So if you use this a dagger in terms of a dagger a, because this is a number operator, okay, it will give the number of nth level of the problem. Okay. So it will be simply, so adding these two, it will be simply twice a dagger a plus 1. So that is equal to twice n plus 1. So number operator, I will put n cap here. Clear? Got it? Okay. So now if you are acting a dagger twice on this thing, so you will get, first you will get n0 plus 1 and then you will get n0 plus 2. Once you are having overlap with n0, that will give you 0. Okay, similarly a square will act on n0, it will lower down it by 2 levels. Okay, 2 values. So that will overlap with this thing, gives you 0. So what is there? Only. So it will be simply n0 twice, let's say n plus 1. Okay, so this will count k by 2. So n acting on n0 will give me n0. So it is twice n0 plus 1. So that means this is the amount of energy shift. Okay, if you see, it is the same thing. What will if you add to your the problem? So you are having your En. So it is En0 plus lambda En1. Clear? Okay, so let's put lambda equal to 1. So that means you are having full perturbation. Okay. Okay. So what you get? So En is equal to, this is h cross omega n plus half. Okay. So this is also equal to, if you take this 2 out, it's simply k. Sorry, I'm using n0, n0 plus half, because I use it n0 to be the unperturbed level. Clear? Got it? So I should have put actually n0 here for the nth level. So now what is the difference? So only so you are having like this, h cross omega plus n0 plus half. So it is simply, you have actually changed the frequency. That means you are adding it. Okay, you can put k. Okay, whatsoever is the value of k. Clear? Got it? Everybody followed it? Okay, great. Any question? Now let's calculate. Yes. Yes, you should ask questions. Especially let me solve this. Okay. Okay, so let's calculate the second order correction to the energy. Okay? Yeah. Huh?
So time is up.
Really? Still 1 minute. We're still 1 minute. Okay. So let's calculate the second order correction to the energy. Now let's look at this very formula. Why is the En2? It is not.
En1.
Yes, it is here. What it is?
En1.
It should be 1.
Yes.
En1, not En2. It should be En1. Huh? Because it should go in this very sequence. Huh? Okay? So this is a sequence. Huh? You can see. So En2 is here. Huh? it comes with the value of energy what you need to calculate at any order of the perturbation, that comes with this n naught. Okay? So what you do now, you just put, okay? So let's calculate, let's have second order correction. Okay? So multiply on left. So you put like this thing n naught. The way we are done with the first order correction, like this thing. No noise, please. X equal to E n naught. Okay? N naught. Okay? So now this object is equal to 1. This object is equal to, this is equal to, clear? Now look, let's look at this thing. This object is also equal to how? So H naught will act on N naught, you will get some N naught back, N naught will N naught, N2 gives you 0. What is your now second order correction? So which implies E N2, that's equal to N naught, H1. Now here is a problem. On what it depends? Second order correction depends upon the first order correction of the wave function. Okay? So that means in order to calculate the nth order correction to the problem, we need to calculate n minus 1th order correction to the wave function. Okay? So we'll do it tomorrow.